In this video I will talk about the second of the two sampling distributions, and this one is known as students T distribution. Right, you may wonder why it's called student. Well, there's a little story behind it. This distribution is actually due to a British statistician. His name is William Gossett. But he worked for the famous Irish beer company. One of their policies was that you're not supposed to publish your research, at least put them in the you're not supposed to put them in the public domain. So that's one of the policies of the company. So he published his findings under the pseudonym Student. So that's how it became known as students distribution. Instead of calling it Gossett's distribution, people have started calling it students T distribution. Anyway, okay, so that's the story behind it. A random variable x has the student T distribution, which I will denote by this letter little t. In bracket A is the only parameter, which I will explain in a minute. If given by, so the PDF of the student T is given by the following. Right, and here the gamma function is, I think I mentioned this in the preliminary. If you look at the preliminary material of the YouTube channel, you will see what the definition of a gamma function. There's a video explaining the definition and properties of a gamma function. All right, the domain of this PDF is from minus to plus infinity. The only parameter A must take positive value, and once again, just like in the previous video, the A is known as the degree of freedom parameter. Okay. All right. Now. And there's a close resemblance between the students distribution and the normal distribution, and I will explain that in this slide. Right. Okay, in this slide, I'm gonna show you how the normal distribution and the T distribution match up each other. So So I've drawn two curves here. One of them is the PDF of the normal variable. So the one in black is the PDF of standard normal variable, and the one in red is the PDF of a t variable. Right? You see, they look very similar. They look very similar in the middle. When I say middle, I mean this part. They are both symmetric and both of them are centered around 0. So although it doesn't look, I mean, that's because of my inability to draw good pictures. Both of them are symmetric around 0, and both of them are symmetric around 0, right? But there is one big difference in the tail. That when I say tail, I mean this area or this area. The PDF of the standard normal variable decays to 0, right, much faster. Right, as you can see, this is the black. The one in black is the standard normal. So they decay to 0 much faster than the PDF of the student t distribution, right? And the PDF of the t variable decays to 0 much slower. So this is the main difference between the two. Apart from that, they look almost the same. I mean, especially the middle part of the picture, they look more or less the same, right? Okay, right. The next slide, I'm going to talk about R commands for computing the first. I will talk about the command for the PDF, which is dt. D stands for density, T stands for t distribution. Open bracket x comma df. Df gives the value for a. So let me take it to be 2. So this command will compute the PDF of a t distribution with a degree of freedom, with 2 degrees of freedom at x, right? And this command pt it computes the CDF of a t variable with 2 degrees of freedom at x. Right? Okay. And in the next slide, I will talk about percentiles. You may recall that in the video on chi-square distribution, I talked about percentiles. So just like that, I'm going to talk about percentiles of the t variable. Right? So first of all, I will give you the definition. The percentile for a t variable this is the notation I will use, and is defined by this statement, that the probability that a t variable is less than or equal to alpha, right? And this is known as the alpha percentile of a t variable, right? So graphically, once again, if I can draw a picture here, let me see if I can draw. Well, suppose this is the PDF of a t variable. Right, so this is the PDF of TA, right? And suppose you have a point here, say here, and to the left hand of this point, to the left hand side, to the left hand side of this point, suppose this area here is alpha, right? Then this point here must be equal to the alpha percentile of a t variable, right? So in other words, the area to the left of this point must be equal to alpha, right? So to give you a couple of examples, one, suppose you want to find the 95th percentile of a t variable with 1 degree of freedom, right? To do that, there are tables, right? Just like there are tables for the chi-square distribution, there are tables for the t distribution too. So to figure this out, we will use this table here, right? So you're looking for 0.95 and 1. So you look for 0.95 in the third column, and 1 on the first column. So you get this number 6.314, right? So the answer is that this is equal to 6.314. So in other words, what this means is that the probability that a t variable with 1 degree of freedom less than or equal to 6.314 is equal to 0.95. Let's look at a second example. Suppose you want to find the 1 percentile of a t variable with 10 degree of freedom, right? Now, there is, if you look at this table here, there is no 0.01 on this row. This is all 0.9, 0.95 up to 0.9995. So to do this, you need to use a property of a t variable, which is the following, that one property of a t variable is the following, that is, if you're looking for t alpha of a, right, this is the same as minus of t 1 minus alpha times a. The reason that they are, I don't expect you to prove this, but the reason that they are equal is because of the symmetry. Is because of the symmetry of the density. Right, so using this fact, you can write this as minus of t 1 minus alpha, which is 0.99. Okay. Now you can go back to the table and look for 0.99 and 10. So 0.99 is this column here, and 10 is over here, right? So you have this number here, 2.764. So you get this is equal to minus 2.764. All right. So these are just two examples on how to read the percentiles of a t distribution, right? So once again, what this means is that the probability that a t variable with 10 degree of freedom is less than equal to 0.01. Okay. All right. So this is the section on percentiles, and the next section I'm going to look at is properties. All right. So if you have a variable x that has a t distribution with a degrees of freedom, then the following properties are true. Number one, the expected value is 0. Number two, the variance is a divided by a minus 2. Number three, that this, a t variable with a degree of freedom, approaches a standard normal variable as a approaches infinity. Right? So in other words, when the degree of freedom gets larger and larger and larger, the t distribution approaches the standard normal distribution. Okay, number four, suppose you have IID normal variables with 0 mean and variance sigma squared. When the following is true, then for later purposes I'm going to call this star. I'll read it later, where x bar is the sample mean, so and S is the sample standard deviation, and there are two formulae that I gave you earlier, so I'm going to use the second of the two, where you have n minus 1, not n. Okay. Right. Now, this result, right? If you look at the right-hand side, it has the t distribution. If you look at the left-hand side, what you have is a function of the data only, right? So this result explains why the t distribution is a sampling distribution. In other words, let me write it down. The left-hand side of star, right, is a function of data only. So it only involves the function. There's nothing on the left hand side that does not involve data, right? Okay. And the right hand side the t-distribution. The right hand side is the t-distribution. So this is exactly why the t-distribution is okay. This is exactly why the t-distribution is a sampling distribution. Right? Okay. So that's property 4. So these are the 4 properties I would like you to know for the t-distribution. Once again, I don't expect you to know the proofs of any of these properties. So let me write this down. Need to know the proofs of these properties. Okay. So I expect only you to be able to apply these properties, not try to prove them. Right? All right. Just to complete this video, I will just do one example. Okay. We want to find the probability that x bar minus 1 is less than s, where s is the sample standard deviation with the n minus 1 in the bottom, not n. Okay? So let's see how we can do this, right? Now, I don't know whether you remember, you should look at the video on the normal distribution, right? Here we have a random sample from a normal with 1, 1. X bar, which is the sample mean, one of the properties I gave you is that if you have a random sample from normal, then the sample mean also has a normal distribution. In this case, it will be with mean equal to 1, the variance equal to 1 divided by n. So this is using a property of normal distribution. So you should go back to the video on the normal. You will see this property that I have used. Right? Now this variable minus take away 1 is gonna be normal with 0 mean and variance 1 over n less than s. Okay. Right? In the next step, I'm going to do the following. see, I had divided both sides by S, right? Okay, in the next step, I'm gonna multiply both sides by root of n. So I'm going to multiply the left hand side by, sorry, excuse me, is normal and the right hand side by root of n also, right? And in the next step, I'm going to write the left hand side as follows. Alright, and in the next step, I'm going to use the property which I call star. You may recall, if you look at the previous slide, you will see there's a property, I think it's number 4, which I call star. Using that property, what you have here on the left hand side is a t variable with n minus 1 degree of freedom. Okay, so this you can write as f t n minus 1 root of o. Okay, so where okay. Alright, so this completes the example and also completes the video on the student's t distribution. And in the next video, I shall talk about a new topic which is known as point estimation, because so far, everything we have done so far is to talk about distributions, talk about summary statistics and graphical displays and so on. But what we haven't talked about so far is how to construct estimators and how to study properties of the estimators. And I will begin that in the next video.